Hi, welcome to another lecture on pre-calculus. Today's topic is sketching the graph of y is equal to a times sine of x or y is equal to a times cosine of x. So we are starting the section on graphing of trig functions. This is a lengthy and important section in the course. We are going to first deal with sine and cosine. Then we are going to generalize to other functions. And then we are going to see what happens if we want to transform these functions. Transforming means like multiplying them by some number, as you see here. For example, 3 times sine of x, or minus 1/2 sine of x, or minus 5/2 cosine of x, or here 1/2 cosine of x. In the future lectures, we are going to look at other modifications we can do to these functions. But before we get started on that, let's just quickly review the graph of sine and cosine themselves. Before we get to this modification, how about the original? What does the original graph come from? So I'm going to start this lecture by just attempting to explain the graph of sine of x. So suppose we want to graph y is equal to sine of x. Let's go ahead and review some basic facts. Our graphs that we are going to do in this section are all based on radians. It's assumed that we are measuring our angle in radians. If you look at the graphs in this section, you see pi, 2 pi, 3 pi, etc. on the axis. So that's going to be the typical for these graphing and also in calculus. So let's just quickly go ahead and review what radian was. So the idea of radian was we take the radius of a circle laid on the side of the circle itself. So if this is the radius r, we pick a string of length r, put it on the circumference, and when we connect this thing to the origin, that is 1 radian. And of course, when we go around the circle, here's 2 radians, 3, 4, 5, 6, and change. This turns out to be 6.28 radians. In reality, that's just 2 pi radians. So if we take the circle and put a string around it and come around, we see that we have used 2 pi r. So circumference is 2 pi r, and we are using 2 pi r length of the string to go around the circle. Now, to make the matter a bit simpler on us, we are going to assume that the radius is just 1. So we call that unit circle. So to reduce the clutter, we concentrate on a circle of radius 1. Now, when we have this circle, do you remember what was sine and cosine? So by now, we have taken that the radius is 1. We have some angle theta. And then we go ahead, pick a point here, and we set the coordinate of that point, cosine of theta and sine of theta. So let me color coordinate these things perhaps. This is cosine of theta. If we drop a perpendicular and look at this adjacent, so let me draw a bigger picture here. So this is the angle theta, this is a radius is equal to 1. This adjacent is cosine of theta, and the opposite is sine of theta. Theta itself, we said, is in this circle we go around this thing in a circle, the length of the string that's played here, that is equal to theta itself, because length of the arc subtended by the angle is the size of the angle times the radius. So the radius is 1, the angle is theta, this length is also theta. So when we are saying graph y is equal to sine of x, what we have in mind is that if you consider an angle x, we put that on the horizontal, on the vertical we are going to put sine of x. So if we put the x on the horizontal, we put the sine of x on the vertical, and that's going to be as we collect more and more of these points, we get the graph of sine of x. When x is 0, well, the sine of x is going to be 0. So you start at this location. When x becomes pi over 2, so pi over 2, same as 90 degrees, at that point sine becomes the largest it can be. So at the point where x becomes pi over 2, sine becomes 1. Sine of pi over 2 is equal to 1. As we increase our angle past pi over 2 and come back to pi, our sine is going to decrease and come down to 0. So by the time I hit pi, my graph has gone up, and then it comes down. So I should do a better job of graphing this. Then what happens? Well, as my angles passes pi and I come to the third quadrant, if I'm here, then the sine, which is this vertical, becomes negative. Sine becomes negative until it reaches its lowest point at 3 pi over 2, at which time my sine becomes minus 1. And then as I march forward, an angle gets bigger. By the time I come back to 2 pi, I have reached back at 0 again. So let me draw this all over again. So I will draw my horizontal axis, going to be longer. Now I start at 0. We have a significant event at pi over 2, another one at pi, another one at 3 pi over 2, and another one at 2 pi. So you see these 5 numbers showing up over and over again when we are graphing these trig functions, because important things happen at these locations. So at 0, sine is 0. At pi over 2, sine is 1. At pi, sine is 0. At 3 pi over 2, sine is minus 1. At 2 pi, the sine is 0 again. So we have these 5 points that are like significant points of a graph, and then our graph goes through these points, and that forms one cycle of sine. What do you mean one cycle? We mean that, well, if you increase the angle again past 2 pi, if you go pi over 2 more, so that's going to be 5 pi over 2. You reach 1 again, and then if you go to 3 pi, you hit 0, and if you continue again to 7 pi over 2, we hit minus 1 again, and if we go to 4 pi, we are back to 0. So what we have in this block, this is called one cycle, or this is one fundamental cycle of the picture. You can think about it as a tile, that if you take this tile, like you make a tile like this, and put that right next to itself, that's going to be the second tile, and so on. You can put infinitely many tiles next to each other, and that would be the graph of sine of x. So this is y equal to sine of x. Let's go ahead and take a look at this thing on a software called GeoGebra. We can look at these functions and get a very good impression of what they do. So here I'm going to go ahead, take a look at this GeoGebra page. It's by Mr. John Golden. So here he is showing to us what happens when we graph either of these functions. So you can click on the sine and either cosine, and you can have the trace on or the trace off. We have the trace off first. What happens as I move? So on this green dot, as I move it, you see lots of numbers showing up. First of all, this arc itself, that's the angle theta. This angle that's in a blue or teal color here, you see the size of it here, for example, reported as 0.61. So that's the length of the string we are putting on the circle. We are taking that and putting it horizontally on the x-axis. What is this red line? This red line represents the sine of theta. Theta itself is this teal color, and this red one is the sine of this red thing. So this is calculating the sine of that angle. I draw that sine in this location. As I change my angle gets bigger. You see that that red length also increases. By the time I come here, you see that the blue or teal color is 1.57. That means pi over 2. Sine of pi over 2 is what? Sine of pi over 2 is 1. So when this length is pi over 2, I want to look at a height of 1. And so on. If I go all the way to here, I've got to pi. Well, sine of pi is 0. And this is my angle, and the sine of it is 0. If I continue, see that the teal color is increasing. By the time I come here, it's 3 pi over 2, and my sine is minus 1. I continue going. I am now at 2 pi. At 2 pi, my sine becomes 0. Now, let me turn the trace on, see what happens. Let's do it again, so we don't lose the memory of all the locations we were at. As I go up, again, remember that this teal color is the angle, and the red one is the sine of that angle. We take the angle, put it down here as x, and the sine of that angle as y. Point by point, we are constructing this graph. As I move around, again, by the time I come to pi over 2, I reach my highest point. Then I start coming down from that mountain. Red color is shrinking. By the time I hit pi, I have come all the way back to the x-axis. Now the red color becomes negative because I'm now below the x-axis. My angle is increasing. By the time I come to 3 pi over 2, my angle is 3 pi over 2. My sine is minus 1. As I keep going, I'm going to hit 2 pi. At that point, sine is equal to 0. So this wave looking graph is graph of sine of x, and we want to be very familiar with it because it's going to be basis of many things that we are going to do later on. We can do the similar thing. We can click the sine off, click cosine on. Cosine, you can do the same thing. Again, the teal is the angle. Cosine is this blue color line here that you see here. This is cosine of x. We are drawing it vertically. So as I go around, you see cosine starts at 1. By the time I reach pi over 2, cosine becomes 0. By the time I reach pi, cosine has become minus 1. When I come to 3 pi over 2, cosine is 0. When I hit 2 pi, cosine comes back to 1. So that is the graph of cosine. Graph of sine and cosine are shifted version of each other, meaning if you take the red and shift it, you get the blue, or if you take the blue and shift it, you get the red. We are going to see that shortly. So let's go back to our problem. So that is how we understand sine and cosine. We need to understand that very well before we continue with these problems. So these problems all assume that you already know what sine and cosine graphs are. What they are doing is modifications of those. What modifications do we have in mind? In this case, we are multiplying our graph by some number. That is called scaling. Scaling, stretching a graph, is a kind of scaling. If you take the graph and squeeze it, that's also scaling. So we have two kinds of scaling: multiplying by a number larger than 1 or multiplying by a number less than 1. We also have reflection, which I'm going to talk about. Let's go after the first example, y is equal to sine of x. So we said these 5 points are the significant points for us. 0, pi over 2, this is pi, 3 pi over 2, and 2 pi. We said for the sine, at pi over 2 we hit 1, here 0, at 3 pi over 2, let me clean this thing so I can have my graph. So this was 3 pi over 2, and at 2 pi we are 0 again. So the graph of the sine looks like this. So this is y is equal to sine of x. Well, what if I take this thing multiplied by 3? So instead of reaching height of 1, I will of course reach height of 3. What if originally it was 0? 3 times 0 is still 0. 3 times this 0 is also 0. 3 times minus 1, minus 2, minus 3. 3 times 0 is again 0. So I have this point, this point, this point, this point, and this point to connect. So I have 5 points to connect to each other. So I'll be going way up, then come down, come to this point down here, build all the way back up. This becomes y graph of 3 sine of x. So what we are doing here is a vertical scaling. Vertical scaling, each y became 3 times as big as it was before. Each y value changed by multiplying by 3. X's did not change. So the way your software explains this thing is to say, okay, make a table. So a table, here are our famous angles to go through, easy angles. So if you were just dealing with sine of x, this would have been 0, 1, 0, minus 1, 0, but all that's happening here is that you're dealing with 3 sine of x. So here y is equal to sine of x, here y is equal to 3 sine of x. All these quantities are tripling, 0, 3, 0, minus 3, and 0. And that does it. Okay, how about minus 1/2 sine of x? Well, here we are doing two things. One is shrinking the graph by a factor of 1/2, and the other one is that we are multiplying by minus. Physically, it means two things. This is a shrinking event, shrink by 1/2. Minus means change of y to its own negative, which is reflection in x-axis. So let's do step by step. So again, we have pi over 2, 3 pi over 2. I don't label them anymore to avoid crowding. Our original picture is going to 1, come to 0, goes to minus 1. So this was graph of y is equal to sine of x, like the grandfather of all of these things. When I multiply by 1/2, instead of going to height of 1, I'm going to 0. And then I go to 0. 0 times 1/2 is 0. Minus 1 times 1/2 is minus 1/2. So the red one is 1/2 sine of x. But that's not what we are after. We are after minus 1/2. So at pi over 2, instead of being half, we want to be minus 1/2. Zeros are always zeros. At 3 pi over 2, we were minus 1/2. Now become plus 1/2. So our graph is going to look like this. So this is the graph of this final answer. Y is equal to minus sine of x. Of course, when you're answering this type of problems, you do step 1 and 2 in your mind, and this is the final answer. That's the only thing we are drawing here. Y is equal to minus 1/2 sine x. However, on paper, if you want to show your work, your reasoning or something, then you so this is our final answer. So on. Well, what about cosine of x? Let's just quickly mention something about cosine of x as well. So cosine of x, again, let's suppose that this is pi over 2, and this is pi, this is 3 pi over 2, and this is 2 pi. And this is our 0. Cosine of 0, we remember that is 1. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is minus 1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1 again. So our picture looks like this. Well, let me do a better job of this. So this is graph of y is equal to cosine of x. You have to keep in mind that the table that goes with cosine, x goes 0, pi over 2 pi, 3 pi over 2, and 2 pi. Cosine of x, cosine of 0 is 1, pi over 2 0, minus 0, and then you're back to 1. So that's the basis of the graph. And then suppose you want to graph 1/2 or minus 5/2 sine cosine of x. So let's just remind ourselves what the graph itself looks like. These are the 5 points of it. If you want to remind yourself of the table, exactly what we wrote up there repeat that again. 2 pi. So cosine of x is 1, 0, minus 1, 0, and 1. When you are dealing with minus 5/2 cosine of x, you're just multiplying all of these things with minus 5/2. So this is minus 5/2, 0. This is plus 5/2, then again 0, and then again minus 5/2. So let me draw the original. Now multiply it by minus 5/2, that's minus 2.5. So this is minus 2.5. So that's, I came down here. 0, 0, well, this is 0. At pi, it was plus 5/2. It's going to be, here's 1, 2, and 2.5. Up here, 0 again, and then I come down to, so my graph is going to look like this. Something like that. That's going to be our final. So this minus 5/2 cosine of x. Let's try one more. 1/2 cosine of x. Well, this is easy. So here's 1, 0, minus 1, 0, and 1. That is the, if you wish to call it, the grandfather of the cosine curves. Multiplying it by 1/2, what you have to think about shrinking it by a factor of 1/2. So it's scaling. What kind of scaling is it? It's shrinking. So if you want to have a visual impression of this, imagine graph of cosine of x drawn on a stretched rubber surface, like you cut a, you take a balloon, say, the material of the balloon, and then you stretch it, make it some big sheet out of it, nail it down on the x-axis so it doesn't move up or down, and then if you let this thing shrink by 1/2, okay, it was originally stretched, now you let it shrink. If you let it shrink, what happens? The graph also becomes shorter, and that's what has happened here. Is from this black, the original curve here is y is equal to cosine of x. You let it shrink by half of its size, so it becomes 1/2. The red one is the final that you're going to get is 1/2 cosine of x, as opposed to like in this first example, 3 sine of x. If you take that rubber sheet and stretch it so that it becomes 3 times taller. So here the black one is drawn on the original rubber sheet, and then we stretch it by a factor of 3. The new graph is going to look like a graph of 3 sine of x. Okay, so to understand this problem, we need to understand the graph of sine and cosine. The number in front is the multiple by which the graph is being scaled vertically. If that number is larger than 1, it's going to become taller. If it is positive and less than 1, it's going to shrink to that height. If it is negative, in addition to whatever else we are doing with scaling, we are also flipping it upside down. Okay, you want to practice this and be able to graph these things, each of them under 1 minute. Practice over and over again until each graph you can do it in under 1 minute, and make sure you understand what happens at these critical points at 0, pi over 2 pi, 3 pi over 2, and 2 pi, and understand the role of a in each of them, and then we'll be good to go. Okay, until next time, good luck and God bless.